Let's talk about Lagrange's theorem, which is a key result in group theory. It's important because it tells us about finite groups, and also because we can apply it then to examples of groups. So for example, it's really helpful in number theory, and it says let G be a finite group and let H be a subgroup of G. It's really important that G is finite here. And then the order of H, the number of elements in the subgroup H, divides the order of G. So my picture of what's going on in this theorem is that we have our group, something a bit like this, and then we have some subgroup of it, H, tucked in somewhere, and we have these things called cosets, left cosets, which are like translates of H. And my picture is something a little bit like this. And to prove Lagrange's theorem, what we'll do is we'll show that this is the right picture. We'll show that indeed the left cosets of H partition G, and then we'll show that each left coset has the same size as H, which makes sense because really they are just translations. Once we all know they have the same size as H, then we know that the size of H will divide the size of G. So first of all, let's have a little claim that the left cosets of H partition G. And to prove this, we need to check various things. So we need to check that each left coset is non-empty. We need to check that between them they cover the whole group. And we need to check that they're pairwise disjoint, that no two overlap. So let's just do that. So non-empty, why is that? Well, we know that little g is contained in the left coset little gh for all g. So certainly each coset is non-empty. And in fact, that also shows us that they cover. So since little g is in this left coset for all g, we have that the union over all g in here of these left cosets is just the whole group, which is great. So that just leaves us with the pairwise disjoint property we want to show. And so if I take two elements of my group G, then we'd like to show that either the intersection of those cosets is the empty set, they're disjoint, or they're the same left coset, because we can represent a left coset in many ways potentially. So let's imagine we're not in this case, so let's suppose there's something in the intersection, let's call it G. So let's suppose G is in the intersection of these two left cosets, and then our aim is to show that the left cosets must be the same. And we have a strategy for showing that two cosets are the same, using the coset equality test. So what does it mean to say G is in this intersection? It means that there are H1 and H2 in H, such that G is equal to G1, H1, so it's in this left coset, and also it's in this left coset, let's say it's G2, H2. So if I multiply on the left by G2 inverse and on the right by H1 inverse, I discover that G2 inverse G1 is equal to H2, H1 inverse, but now H is a subgroup, so certainly H2, H inverse is contained in H, and now we're in good shape. So by the coset equality test, we have that these two cosets are the same. This is exactly the condition we want. So coset G1H is the same as the coset G2H. So that proves claim 1, which tells us that this is the right picture somehow. What I would then want to show is claim 2, which is that each left coset of H has the same size as H, so has size order of H. And how do we show this? Well, the natural way is to write down a bijection between each coset and H. So if I take an arbitrary G in the group, then I can define a map F from H to this left coset's GH in the natural way. So I'm going to take an element little h and send it to the element little gh, which is certainly in this coset. And then this is a bijection. So we could check directly that it's injective and surjective, that would be fine, or we could just see that it has an inverse, and its inverse is the map that sends g twiddles in this left coset to g inverse g twiddles, which must then lie in h. So certainly the size of h is then equal to the size of this left coset, and that proves claim 2. So now we can see what the size of our group G is. We see that we have a load of copies of, well, a load of translates of H, each of which has the same size. How many are there? Well, we've given this a name. This is the index of H and G. This is the number of left cosets of H and G. So the size G is the number of these things times the size of H. So certainly the order of H divides the order of G, and that proves the theorem. And maybe we can just notice that actually we get a bit more information here. We discover how exactly the size of H divides the size of G. It's multiplied by this index, and that's sometimes a useful piece of information. So one little health warning is it can be very tempting to hope that there's a converse of Lagrange's theorem, that if we've got some number that divides the order of the group, then there's necessarily a subgroup of that order. And in general, that's just not true. There are lots of counterexamples of that. So in specific cases, there are particular results that show that under certain circumstances we can get a result like that, but in general, Lagrange's theorem doesn't have a converse.